Hi everyone, my name is Renjie Zhao, a PhD student of UC San Diego. Today, I'm going to introduce our work, MCube. It is the first mmWave massive MIMO software radio. mmWave technologies represents a cornerstone for emerging wireless network infrastructure and for RF sensing systems in security, health, and automotive domains. Through a MIMO array of phase arrays with hundreds of antenna elements, mmWave can boost wireless bit rates to more than 100 Gbps as proposed in the mmWave Wi-Fi standard 802.11ay, and can potentially achieve near-vision sensing resolution. To conduct research on mmWave massive MIMO, we believe a programmable experimental platform with the following critical capabilities is needed. First, it should be equipped with low-cost and large phase arrays, which represent the key features of mmWave radios. Second, it should support the mmWave MIMO architectures, which is to be used in 5G NR and 802.11ay. Third, fast beam swapping should be available, which allows real-time beam swapping to accommodate the high mobility networking or sensing scenarios. Fourth, it should allow reconfiguration of beam patterns, communication or sensing algorithms, and network stack. Unfortunately, to date, there is no widely affordable platform which satisfies all the capabilities, which is impeding the research in this field. One widely utilized and deeply investigated platform is the commercial 802.11ad access point. This commodity radio device is usually cheap because the cost is amortized due to the large manufacturing volume. But the available information is usually just RSSI, and this signal strength will really limit the capability of the platform to some coarse-grained beam algorithm analyzing or network layer evaluation. Also, it will only be widely available after the standard has been finalized. This is the reason why there is still less MIMO-compatible 802.11ay device being available now, because this standard is still under development. There has been software-defined radio equipped with mechanical steerable horn antennas or omnidirectional antennas. These platforms cannot do the fast beam directional swapping because they need mechanical turning and can be hardly used to investigate the severe problems of high mobility scenario. Other researchers have also developed mmWave platforms based on self-built phase array, such as the OpenMILI project, or purpose-built front-end with discrete components, such as mmFlex or X60. This kind of design is typically expensive, and none of these existing platforms support mmWave MIMO configuration due to the limitations of this RF front-end. The NI mmWave testbed can be used to build up a 2 RF chain MIMO setup with third-party phase arrays, but the cost of over $100 per RF chain limits its adoption. Our MCube platform represents the first mmWave MIMO software radio to overcome these limitations and meet the aforementioned critical requirements. Our main idea is to convert a commodity multi-chain 802.11ad radio to an SDR, so that we can take advantage of the low cost of commercialized antenna array while keeping the flexibility of SDR. mmWave devices do not follow the normal microwave radio architecture, which directly routes RF signals from RF chains to the passive antenna. Instead, as in the 802.11ad and 5G NR chipsets shown here, commercial mmWave devices will have an active phase array, and the cable between the two parts will route in IF signals, which suffer less from the cable loss. To convert the commodity radio into an SDR, we need to first reverse engineer the architecture of the commodity mmWave devices. This figure shows our reverse engineering setup, which aims to measure the signal between the baseband module and the phase array module. Let's zoom into the detail of the spectrum. We found that there are mainly 4 signal components going through the cable. The DC voltage is the power supply of the phase array. The control signal is used to change the state of the phase array, such as changing gain or beam pattern. The 7.5 GHz reference clock acts as the clock source for the phase array, and the 15 GHz RF waveform, which is going to be converted to the mmWave band. Based on the measurement findings, the architecture of 2 modules can be reconstructed like this. Briefly speaking, both the data signal and phase array control commands are generated by the baseband module. If we can hijack the coaxial cable and replace the baseband module with a customized data and control signal generator, then we can convert the entire radio into a software-defined radio. We thus build MCube following this design principle. MCube consists of the commercial baseband module and phase array module, RF bridgeboard, baseband processing unit, control FPGA, and the host PC. First, we will talk about the flexible data path design. The key components here is a bridgeboard serving as the bridge between the baseband data processor and the phase array module. 2 signal paths go through this bridgeboard. There is a direct connection path 1 between the baseband module and phase array module, which is going to reuse the DC, control signal, and the reference clock. The second path is to use the reference clock as the local oscillator and convert the baseband waveform to the 15 GHz RF signal. The bridgeboard can work with 2 typical types of baseband processing unit. First, it can be interfaced with a wideband ADC or DAC and the FPGA. The 2 baseband ports will be connected to the I and Q paths. Then the RF bridgeboard will act as a direct IQ converter. Second, it can be connected with other SDRs such as warpboard, USRP, which have been widely used by other researchers. One concern about the bridgeboard is whether it degrades the signal quality. We conduct an experiment to answer this question. We compare 2 kinds of connections. The first one is direct connecting the TX and RX of the BPU, which acts as the ground truth. The second one is adding the TX and the RX bridgeboard. The BPU we use here is the USRP N310, and we vary the carrier frequency of the N310, then measure the SNR. The result shows that for any baseband signal below 3.5 GHz, the bridgeboard barely introduces any SNR loss. This means the bridgeboard can accommodate up to 3.5 GHz of baseband bandwidth without noticeable SNR loss. Then we measure both over-the-air and loopback SNR with different types of BPUs. Different BPUs have different sampling bandwidth. We found that for most of the BPUs, the over-the-air SNR performance is very good as long as the sampling bandwidth is large enough. The main SNR loss is introduced by the RF front end of the commodity mmWave radio, so the over-the-air SNR is similar among different BPUs. The control path of MCube is generating commands to control the beam patterns of the phase array with low latency. Control commands can be sent from the existing baseband module on the commodity mmWave radio, but this will introduce around 40 millisecond system-level delay, which is too long for beam swapping. As an example, scanning 32 beams will take around 1 second, but what we want is sub-microsecond level latency. Therefore, we choose to use an external control FPGA to send the real-time beam control commands, which passes through the path 3 on the bridgeboard. This design also enables 2 new capabilities. One is to configure the multiple phase arrays on the mmWave MIMO radio to different states, such as different beams or different RF gain at the same time. The other is to configure the phase arrays to the radar mode, which means one array is set to TX and the other as RX. The final control path connection is like this. First, the BPU, for example the USRP N310 here, provides a trigger to the control FPGA, which indicates the BPU begins sampling baseband signals. Then the control FPGA will send out the control command to configure the beam pattern. As shown in the figure, the total delay will be less than 1 microsecond, which is comparable to the beam control latency on a commercial non-programmable mmWave radio. Then we investigate the phase array module to make the beam pattern reconfigurable. The phase array in the commodity mmWave radio is a uniform planar array. We conduct extensive calibration to find out the mapping of the antenna element and the codebook entry. Then we can program the codebook corresponding to the beam pattern we want. The figure shows some examples, where we generate narrow beams pointing to different angles by using all the antenna elements. Or we can generate wider beams pointing to different angles by using some of the antenna elements. Finally, we can easily extend the above architecture into a massive MIMO mmWave radio or radar. There already exist commercial 802.11ad mmWave radios with multiple phase arrays but a single RF chain. For example, the 802.11ad radio we use in MQ has 8 RF ports connecting to 8 phase arrays. These ports share the same carrier clock and data path. In MQ, we repurpose such multi-array radio into a multiple RF chain MIMO architecture. As shown here, different phase array modules are connected to different RF bridgeboard and sharing the same control FPGA. But they can use separate data channels on the BPU to realize MIMO configuration. Putting everything together, this figure illustrates an M-cube node with TX and RX bridgeboards and a 4RX MIMO setup. This MIMO architecture provides unique research opportunities for 5G mmWave networking and sensing. First, our array of phase arrays architecture let the platform can be used for multi-user or single-user MIMO, channel estimation, and MIMO radar. Then, the real-time control for fast beam swapping and data collection give the opportunity to conduct MIMO experiments under high mobility. Here, we can conduct a few case studies involving the mmWave MIMO hybrid beamforming capabilities. mmWave MIMO hybrid beamforming generally operates in 2 stages to realize hybrid beamforming. First, it selects the best beam indices for each phase array, which is doing analog beamforming. The IEEE 802.11ay test groups have proposed 3 possible algorithms for this first stage: exhaustive, K-best, and evolutionary. We adopt the 3 algorithms for our case study. Second, to measure the channel with the selected beams to achieve either diversity or multiplexing gain, which corresponding to digital beamforming. This is pretty similar to legacy MIMO in 802.11ac. As one case study, we evaluate 2x2 mmWave MIMO performance in a multipath reach conference room and a multipath pool outdoor environment. A metal box is placed in between to create a non-one-offside blocking effect. We used N310 as BPU and collected a channel state of all possible combinations of beam selections in a reasonable amount of time. And we used the data to do the following algorithm evaluation. This figure shows the comparison of the capacity for diversity and multiplication gain in these scenarios, while using the same beam training method. We observed that the multiplexing capacity is around 50% higher than diversity capacity in the indoor environment, but around 30% lower in the outdoor line-of-sight scenarios. However, in outdoor non-line-of-sight scenarios, multiplexing achieves higher throughput. Overall, multiplexing gain is most prominent in multipath reach and non-line-of-sight environment. This result shows that it would be beneficial to adaptively select the digital beamforming mode based on the channel content. As a recap, MCube can reproduce the most unique aspects of mmWave radios in a programmable manner. It enables experimental research in mmWave communication and sensing with unprecedented flexibility. Compared with state-of-the-art mmWave platforms, MCube supports larger bandwidth, contains multiple phase arrays for MIMO, and a larger phase array. It can be connected with microwave SDRs and can do fast beam swapping. It also has many times lower cost. To summarize, MCube represents the first mmWave massive MIMO software radio. It has been open sourced and can be easily reproduced. We are also distributing MCube replicates to other research groups. Please refer to the project website for more information. Thanks for your attention.